how many complex numbers z have positive imaginary part, and the value of function f of z has real and imaginary parts that are integers with absolute value at most 10. Let z equal x plus iy be such a complex number. The target complex number n plus im is the value of function f of z, where n and m are integers from -10 to +10, and we assume that y-coordinate of number z is a positive real number. We'll rewrite the equation that we have in the previous diagram in the standard form of a complex number, and we'll write two separate equations, one for the real part and the second one for the imaginary part. Then we'll solve them for x squared and x, and we'll make one substitution. We'll use a new variable t instead of x squared. If in this formula y equals 0, then x is equal to m. And since y must be positive, x and t variables belong to the intervals shown on this diagram, depending on the sign of m. This diagram shows the graph of this equation with positive m. This is the graph of the same function with negative m. And this diagram shows the graph of this equation when m is equal to 0. The y-coordinate can be any positive number. And this is the graph of the equation t equals m over 2y plus 1 squared when m is positive or negative. In case when m is equal to 0, the graph is the positive part of y-axis, as we saw in the previous diagram. This picture shows the positive section of the graph of the first equation, shown in black color, and the graph of the second equation from the previous diagram, shown in red color. Now let's count combinations of m and n such that these two curves intersect and produce a unique point with coordinates t and positive y. This corresponds to 2 points x equals plus and minus square root of t and positive y that are distinct if t is not equal to 0. We can see that the two curves cross if and only if the leftmost point of the black curve is to the left of the rightmost point of the red curve. In other words, if n minus 1 is less than m squared. For m equals 0, there are 11 such black curves. The one that starts at minus 11 when n equals minus 10, and the last one that starts at minus 1 when n equals 0. Note that the origin of coordinates 0, 0 cannot be counted as a solution because y-coordinate of complex number z must be positive. For m squared equal to 1, there are 12 such curves. When m squared equals 4, there are 15 such curves. When m squared equals 9, there are 20 such curves. And finally, when m squared is greater than 9, that is equal to 16, 25, 36, etc. up to 100, then all 21 curves with n from minus 10 to plus 10 have the value of n minus 1 less than m squared. For each curve except when m squared is equal to 0, we must count two pairs of coordinates, n m and n minus m. So we count 11 such pairs for m squared 0 and multiply all other numbers that we have calculated earlier by 2. The result is 399. The answer is A.